We are starting today with virtual memory, which is similar in a confusing way to what we have already done with memory. We did main memory, but the main difference is like this. In main memory, we assumed we had pages, we divided the memory into pages. Maybe we had segments, if you remember, we talked about segments, but always we assumed that when you finally found the address and you went to memory, there it would be what you wanted. Maybe the page wasn't in the TLB. We talked about that. The page, we cached the page tables. Sorry, there's the page table. Maybe you had to jump around to find it. But when you finally found the memory you wanted, you went to the memory and there it was. Now we're going to add another level of abstraction, which is that the page you want might not even be there. In other words, first of all, you looked in the TLB and you found that the page that you want isn't there. So now you went to the page table and you found that where it actually is. And now you go there, but it's not even there. It's not in main memory. Where is it? Where could it be if it's not in main memory?
Virtual.
Where? Yeah, okay. Virtual memory, exactly. Yes. It's in virtual memory. What does that mean? It's in the air, it's floating around, it's angels?
That is on a computer.
On a computer or where? Hard drive. I heard the word hard drive. Say no more. Hard drive. It's on the hard drive. In other words, I go to memory, it's not there. Oh, it's in the hard drive. I got to bring it in from the hard drive to memory, and then I can access it. So it's going to slow everything down.
Like that's what virtual memory is?
That's the idea of virtual memory in a nutshell. So
let's see what 70% is there.
Background. What we have seen in the previous chapter has assumed that all the program code is in memory. This makes sense since code needs to be in memory to execute. But entire program rarely used. In other words, we don't usually use the whole program. It might be sensible to have some of the program not in the memory, but just on the disk. Error code, unusual routines, large data structures. Entire program not needed at the same time. Consider ability to execute partially loaded program. Program no longer constrained by the limits of physical memory. Programs could be larger than physical memory. Theoretically, I could have a program that the program was larger than the memory I had. I have 16 megabytes of memory, but I have a 20 megabyte program. And how would I run it? In parts. It's like, how do you make, they just made the world's largest a certain kind of cake in Greece. And it was like, a mile long or something. But of course, I always wonder when I hear like this, well, how did they have an oven to bake with a mile-long oven? How did they bake a cake a mile long? They built an oven, so they must have the world's largest oven too. So the answer is no, they just put a lot of little cakes to put them next to each other and put icing on top of it. So it's all baked separately. So same thing here. You could have a large program run in.
It's like when you have like a double decker cake, that's one cake.
Try not computers, go away.
But the point of the mashal is to relate to our example here. You can our oven is in our case the memory of the computer. We have a program that's larger than the oven, so we'll just put part of it in the oven and bake it, and then another part. We'll just put the program into memory in parts. That's the big condition. That the program is not in memory, we're running it anyway. We're running the part that we need.
Okay.
That's the idea in a nutshell. Question is how we do it. Virtual memory is a separation of user logical memory from physical memory. Now, the way the user or the program views memory is different from the way physically it's laid out.
We already do that earlier with pages.
That was one level of abstraction. Yes, we already did, but it's even more different now. Because now it's not even in memory. Only part of the program needs to be in memory. Logical address can therefore be much larger than the physical address.
Okay.
Because we could actually have a huge memory space for the program or for the logical situation larger than the physical. Allows address space to be shared by several processes. So that means Well, the address space can be, right, they can use the same addresses. What was I thinking about, well, I could have done that before probably. Allows for more efficient process creation. Why does it allow for more efficient process creation? Because when I create a process, normally I have to load it into memory. If the program is large, it'll take me a long time to load it into memory. Even if it's large, but I don't load it all into memory, then I can get it running faster. I can just get the part of it that I want running already running. More programs running concurrently. Also, what if I have enough memory? Here's another point. I have enough memory to put this program into memory, but I choose not to. I want to keep myself some free memory in case another program comes along. I want to be able to give him memory. So I have this program that if I would put him in, he would monopolize all of my memory. I don't want to do that. I want to keep some memory spare for other programs. Virtual memory can be implemented by demand paging or demand segmenting. So demand paging, well, we'll talk about it. Virtual memory that is larger than the physical memory.
So virtual memory is just like the logical memory?
Virtual memory,
Like, because we separated into physical and logical.
yeah, no, virtual memory, the way I'm defining virtual memory is it's memory that is not that is memory for a program which is not in the physical memory, which is actually not there. Let's look at this example. Here's a virtual memory. I have page 0 through, I think V, virtual, whatever, some large size. The physical memory is smaller. Physical memory is 0 through 20, whatever. This is 25. So how do I go about my business? If I want a particular page, I go to a memory map. This is not exactly the page table, but it'll be the page table kind of, but I go to this memory map and it tells me, is the page that I'm interested in page number 2. Is page number 2, is it here? If not, in other words, this page, it says is here. This page, it doesn't find, so it has to go to the disk. This, whenever you see this symbol, this means a disk. This kind of, because it's like a cylinder, is always means a disk. An external, we call that's external to the actual computer. It's in the physical box of it. Every single laptop has a hard drive. It's either there's two kinds of hard drives: SSD, which is a static state drive, or a disk that moves, a rotating disk. Either way, we'll call them a disk, or hard drive. So basically, what I was saying is here, this will tell me where it should be in physical memory, and if it's not in physical memory, it also has to tell me where it is in the hard drive. Notice if I don't find it, I have to have a way. If I don't find it in memory, I have to still know where it is in the hard drive then.
What are the arrows going from the hard drive to the physical memory?
That's just that's swapping.
Oh.
That's bringing a page in or taking a page out.
When does that happen?
Yeah, right. This diagram is not very good. It doesn't really show you a particular scenario. It just shows you general things that go on. Sometimes I find it here. Sometimes this is just saying like this. Sometimes I find it here. Sometimes I find it there. Notice these are both actual memory. I think the white means that it's not memory that I have. The gray means these are actual ones that I have. And sometimes the actual one that I'm using, in other words, this is saying like, my program doesn't even use this location. It uses these gray locations. And this gray location is actually in physical memory. This gray location is not, and I got to go here. Why it's passing through that? I don't know why, but it has to pass through somewhere. It could go around. I guess.
The virtual memory can have an unlimited amount of pages.
The virtual memory has an unlimited amount of pages. Yes, unlimited.
Maps.
Because it'll just map to a smaller. Obviously, the program can't. Well, yes, it can't use more than a hard drive. It's not unlimited.
Yeah.
It's unlimited for the perspective of how much memory I have. The memory is not a limit on me. Hard drive is still the limit. But I can't run a program if I don't have it in my hard drive. I mean, at some point it has to be on a hard drive. It would be hard to run. Okay. Here's the stack. This picture virtual address space. Here's like all the memory of of a program. It's got a stack, a heap, data, code. You remember this picture from computer architecture? This is just the standard picture of the memory used by computer. I don't remember exactly why I have it here.
What's the blue area?
The blue areas just indicate that the stack grows and the heap grows. Now I allot a certain amount of memory to a program and I don't necessarily use it at once. And over time, I increase the use of the stack or the heap. Stack goes down, the heap goes up. They're using the same space though. Okay, the space or hole between the growing heap and growing stack, this stuff, here, now I see why I put it here. All right, the space between this will not require physical memory until assigned. You see that already? We have already an interesting point. I can say my program, this is my program's memory, but he's not using, his stack is empty right now. But I've given him a large space for his stack. Well, that large space is unused right now, so why allocate? I mean, why even allocate it in memory? I'll only allocate it as the stack grows. Enables sparse address spaces with holes left for growth, dynamically linked libraries, etc. So how would we have done it before we had this? We would have had a page for this, like we would have said, let's say, this is the whole program memory. We would have said this, we would have said like the first, this is a one page, another page, another page, another page. I'm intentionally doing it not on the same lines as these.
Yeah.
This will be a page, this will be a page, a page, a page, a page, a page, a page, and I'll have them spread out in memory. But I'll still have this page assigned to this program because maybe he'll need it. So I have it assigned. Now I'll say, no. This page won't even be assigned, and this page won't be assigned, and this page won't be assigned. Because I'm not using them right now.
So it'll skip all of the blue space. essentially.
Exactly. Well, it depends how the page is. If I'm using some of the stack, it might be that I have a page here and a page like that.
Overlap, and then you need.
And I need to allocate a whole page. I can't allocate a part of a page. But more or less, the blue space is what I would like to not allocate. System library shared by a mapping. We'll see that in the next slide. System library shared by a mapping into several virtual address spaces. In other words, I can have a system we talked about this before, but yeah, we talked about this before. Now they'll just be on the disk. It's really, we could have done that before, which is that they can share files. They can share system libraries. Shared memory by mapping pages into several virtual address spaces. Right, I can create shared memory, which means between two different processes, they can share memory by mapping pages into several virtual address spaces. I can have the same virtual address space reference. I can have two virtual addresses reference the same physical page. We could have done that before.
Yes.
We could have done that before. Pages can be shared during fork, speeding process creation. When I do a fork, I don't necessarily. It's true that when I do we learned about a fork. When I do a fork, I create a copy of my process. Theoretically, I'd have to copy all the memory of the process. But what I could do is say, well, I'll just copy the memory that I need right now. And as I go, I'll add more pages. That we couldn't have done before. So here's an example of a shared page. So let's say I have some shared pages that this program and this program both want to use. So they both map to the same location.
But what if like some part of the shared library is?
Because you don't write to the shared library.
No, but what if like the page, the shared library doesn't fit exactly into one page? Like what if some of the shared library is one page and it's also part of like a program? Then you can't share the memory, right? Like a page is half of the shared library and half is the code, something like that. Can't happen?
Oh, I see what you're saying, but no, the shared library will be on have its own page. And I'll just
Okay.
use that page. I'm not gonna put it into my program.
Okay, yeah.
Okay, so what is demand paging? So it's like this. We could not do demand paging. What would that mean? We would bring the entire program from the disk into memory at load time. right? But that would be, let's say we weren't interested in virtual memory. We weren't interested in leaving stuff on the disk. What would we do? We'd bring in all the pages of the program at the beginning. Demand paging says instead bring part of the program enough to fill a page or several pages of memory and guess. So we could say like this: anytime a program is run, we're going to bring in 3 pages. The first 3 pages of the program will start. We'll give him, and then as the program continues running and gets to the 4th page. So now all of a sudden there's demand for that page. We'll bring that in, and as the demand arises, as it continues running, gets to the next line, finally is on another page. Oh, we have demand for that page. We'll bring that page in. So that's called demand paging. As the pages are demanded, we bring them from the disk into memory. We could assume that we'll start off with, let's say, 3 or 5 pages, something like that. This will cause less I/O needed, no unnecessary I/O. In other words, if we would bring in the whole program at once, we'd have to have copying, which is I/O. The operating system would have to tell the some kind of DMA to bring in a whole lot of pages into memory. So we have less need for that, and sometimes we actually may have overall less, because it might be some pages that we never get to. Our program maybe exits before it gets to run all the lines of the code.
Mhm.
And in general, there's a 20-80, 20%, 80% rule. 80% of the time the program is doing 20% of the code. Something like that. You don't necessarily use all the code, because you may have a lot of error code and error handling. You may have a lot of scenarios that never occur. Okay. So less I/O, less memory needed. We're gonna not, at maximum, we'll need all the same memory, but we're not gonna ever need more memory. We'd probably need less. Faster response. The program will seem to be ready to run earlier. When I start to run the program, it'll be ready. It'll be ready. Okay, well, welcome. What do you want to do? It'll already be asking me. It'll be responding to me quicker because it didn't have to load the whole program. And more users. I can have more people running programs because I have more space in my memory now. So page is needed. When is a page needed? When there's a reference to it. When there's a reference to it, it could be an invalid reference. We could be trying to go to a page we're not allocated. Then that would be abort. We'd stop the program. If it's not in memory, but if it's just not available, but it's, in other words, there's 2 possibilities. I tried to get to a page and it's not there. There's 2 reasons why it's not there. One is it's invalid, and the other is it's just still on the disk. So there's such a thing as a lazy swapper, which says like this: never swaps a page into memory unless the page will be needed. Well, that's kind of what we're saying. We never bring a page in until you need it. Swapper, as we discussed in earlier chapters, swaps out the whole program to disk. Now we are talking about swapping in and out only a page of a program. A swapper that deals with pages is correctly called a pager and not a swapper. Swapping, really, we talked about swapping before when we said the program, let's say the computer was running out of memory, we could swap a program out of the ready queue and put him into the disk and say, we're not going to let him run for a certain amount of time and let the other programs run. That was called swapping. So this lazy swapper, we could also call a lazy pager. That's called demand. This, what?
Is that where the term paging comes from?
Yeah.
From this?
What
I
page?
think probably it's like a pager.
No, I think it's the other way around. You're worried that the Israelis will blow us up?
Our operating system is supposed to be.
So here, transferring, swap out, transfer a page memory to contiguous disk space. No, can transfer of, is there any way to get rid of all this stuff?
I was literally thinking the same thing.
I didn't think,
If I put my mouse here, it's supposed to go
maybe
away.
like Alt Z, I think there's some.
Anyway.
Mostly.
Really? Alt Z, I'll try it. I'll try it.
No.
Okay.
It was some.
Transfer of a page memory to contiguous disk space. So we're just saying this program A can be swapped out. We're reminding you of what swapping is. Swapping is taking a whole program and putting it onto the disk, taking another program and bringing it in. that we could do, that we talked about before. Do I talk about pure demand paging? If I don't talk about it, yeah, let me mention something here. Okay, as long as we're, wait, do I mention? Okay, let's go back to this thing, this page about demand paging. There's something called pure demand paging, I should have written it here. What pure demand paging is instead of guessing that we need several pages of memory at the beginning, we say we don't need anything. We just, or are we bringing in the first page of the program? Or we try to run the program and immediately we get that page that it's trying to access is invalid. So we'll bring in the first page. And then we'll start running. And as soon as we get to the next line that needs a new page, then we'll bring it in. So the idea of regular paging, it's a very small difference, but the idea of regular paging, of regular demand paging, I should say, regular demand paging is saying, bring in 5 or 10 pages at the beginning just to get the ball rolling. And then later we'll bring them in. And pure demand paging says, no, don't bring anything at the beginning. Let there be a page fault right at the beginning. A page fault means I try to access the page is not there and bring that in. And only when there's a page fault do I bring it in. That would be called pure demand paging. Okay, so here's the swapping. And now we're talking about this valid bit. So with each page table entry, so we're still having our page table we talked about before. So we have our page table. With each page table entry, a valid invalid bit is associated. Valid means it's in memory or memory resident, and invalid means not in memory. If it's pure demand paging, so initially the valid bit is set to invalid on everything. So that means that's pure demand paging. Every single page is not there. And then he'll bring it in. We talked about invalid valid when we talked about page table before. What did it mean then? What did the valid bit mean when we talked about paging? We weren't talking about virtual memory, we were just talking about
It was a particular use.
what?
The data was data that we took.
Right, if it was assigned to us. If it was a page that was actually assigned to us at all. Because remember, so here
We have 2 valid bits?
Here we have, well, you could think of it as 2 valid bits, or you could say it has a different meaning now. It means it's a page,
I guess we don't care about this.
the page, well, that's what we said before. Now we're just gonna say it's invalid, and invalid invalid just means it's not here. Go get it. And remember what we said over here? If it's not here, then either there's 2 reasons why it's not here. Either it's not in memory, or it's actually invalid. We'll sort of have to differentiate between those 2 cases. But you're right. We kind of need 2 invalid bits. Simplest way to think about it is yes, the two valid invalid bits. One is that it's just invalid because it's not there, but it's really a good page. And the other is it's a page you weren't even assigned. During address translation, if valid invalid bit in page table entry is invalid, then you have what's called a page fault. Okay, explain that. So here you have an example. And here's your logical memory. We're using everything. We're using A through H.
We're calling it a page table and not a memory mapper that we had earlier.
Yeah, well, before we were talking about it theoretically. We were saying it's some kind of memory map.
Yeah.
We didn't yet reveal to you that it's a page table. It's just the same page table that we have. But yeah, that memory map will just say, you know what, their page table will be our memory map. So now, but thank you for following along. So what does this say? Look at this. This is a great picture. A, B, C, are they all here? Yeah, here's A, here's C, and here's F. Where's B? On the disk. See that? Look at the disk. Everything on the disk. You see everything is on the disk? A, B, C, D, E, F, G, H. Everything is on the disk. Only some of it is actually in memory, A, C, and F. So when I try to go to my page table and I say, give me page A, well, A is 0. So go to 0 on the thing, on the page table, and it tells me 4. What does 4 mean? It's in memory space 4, and there's a valid bit. But when I get to one, when I gotta go to page B, it says invalid. So then I have to go to the disk to get it. Now, what's missing from this picture? There's one piece of information, I mean, there's some very missing information here. How do I know where B is?
Mhm.
Right? That's kind of the memory map that you're talking about. In other words, what's not in this picture is, okay, I want B, it's not here, it's invalid, it should be here. Where is it? It's on the disk. Well, where on the disk? Is it in this box? Is it in the first box? Which box is it in the disk? So I need a memory mapping, it's not shown here.
You don't, why can't you just put it in like the one?
No, because
Somewhere.
the disk has. No, I have many programs on disk.
How do you access it from the disk?
Why can't you just put the address of it on the?
Well, well, maybe that's what they mean here. If we have, wait a second. We could say like this, that A is contiguous. Here, look, we could say, well, A is contiguous. So if we know where it starts, we know where all those pages are. And B is contiguous. If we know where it starts, we know where all those pages are. We could have that, but then we still would have to have the beginning of B. We still have to know the beginning where A is and the beginning where B is.
There's no reason why you can't store it in like the place where you normally point to which page. So like, if you look at what is the thing graph that we had earlier?
Remember, the disk is much larger than memory.
So you need much more addresses?
Like, how do you get?
We don't use we don't address the disk in the same way as we address
Okay,
memory.
how do we get stuff from the disk? Are we talking about that at all, or it's not?
How do we physically copy it?
Or
We have a
how do
DM
even
we have a-
access it like logically?
Don't we have DMA, direct memory access? We have a DMA. How we access it by its logic. That's the next chapter.
Okay, so we're not talking about that right now.
We're not talking about that right now.
You keep saying we gotta get it from the disk, but like.
Yeah, right. We're gonna get into this. That's the next chapter. We talk about that a bit. But but in general, we could say that, well, B is contiguous in the disk. So we know where, we still don't know where it starts. In this picture, it certainly looks like it's contiguous. A, B, C, D, E, F, G, H. Doesn't have to be, but if it is contiguous, that's great, but we'll still have to know where it starts. Even if it's not contiguous, so we'll talk about that in the next chapter, how it's spread out, how we can find it all. But still, for example, I'll give you a simple idea. We could in A have a pointer to B. Could be like a linked list. In A have a pointer to B, in B have a pointer to C, and then they could be anywhere. But I still need to know where A is. So we'll still have to, and that's called a directory or a directory, a list of all the files. So we'll still have to have something that tells you where it is. In any case, this is the idea of virtual memory, where you see that A, C, and F are in memory, and therefore when I want to go to F, which is in place 5, I go to the page, it says me 9, and lo and behold, it's there. Page fault. If there is a reference, we mentioned it already, but if there is a reference to a page, first reference to that page will trap the operating system. In other words, when I first reference a page, the operating system will say, oh, the page is not there. So that's a page fault. Operating system looks at another table to decide, is it an invalid reference, in which case it aborts, which is not shown in the previous slide, or just not in memory. If just not in memory, get the empty frame from the disk. Swap the page into a frame via a scheduled disk operation. In other words, if we're gonna, let's say he wants to access page B, we're gonna have to put B into some memory location. We have to find a free location for it. And it may not be so simple. It may be that there is no free location for it. Reset the table to indicate the page now in memory, set the valid bit to V. So in other words, if we put B into some location, we'll have to put a V over here for the valid bit. And then go back and restart the instruction. Because right, the instruction tried to run, it created a fault, it created an interrupt. We had to go bring back the page. Now we got to try to run it again. And hopefully now it'll work. We have the page in memory.
Why couldn't we just like gotten the page while we're turning it to memory? Wouldn't that be faster?
While we're what?
While we're transferring it into memory, why couldn't they have like also taken that page and used it?
We did.
Like, well, why do we have to restart the?
The command got interrupted. It got stopped. It tried to run and it couldn't. The first thing it did was instruction fetch, and it failed. It failed to do the instruction fetch because it got a trap telling it you can't. So now we got to do instruction fetch again. It's all right.
Yeah.
Aspects. Aspects of demand paging. Extreme case. Here we talk about pure demand paging. Start process with no pages in memory. The operating system sets instruction pointer to the first instruction of the process. Non-memory resident. If it's non-memory resident, then we're going to get a page fault. And for every other process pages on, and for every other process pages on first access. So as every time we have a first access of a page, we're going to get a fault, and they'll call it pure demand paging. Actually, a given instruction could access multiple pages. Theoretically, multiple page faults, paying decrease because of locality of reference. So what does that mean? We didn't really see it in MIPS, but let's say I had an instruction that in some computers you could do an instruction like move this memory location to that location. You guys with me? Let's say I'm saying move from one location to another location. Those two locations could be far apart. That could be one instruction. So I could have one instruction that causes me to have two page faults. First of all, the instruction itself is on a different page. And secondly, it's saying move something to some other page. So I need to have that page in memory. So I could have multiple, I could actually have three. The instruction itself could be on a new page. Then it says copy from this page, which is not in memory, to this other page, which is not in memory. So it could be three. I could have multiple page faults. So you say this is bad because it's going to slow me down. When I'm trying to run this program, I'm going to have to do a lot of swapping in the middle. You see, I gained something. I didn't load the whole thing into memory in the beginning. So my program started running faster. I got faster response time. But I lost something too. Now runtime will be slowed down. Because while I'm running, I may need to stop what I'm doing and bring a page in from memory. So what I gained in startup time, I lose a little bit in runtime. But there's something called locality of reference. What that means is that generally speaking, programs stay within their location. Same way that a person generally stays near his house. He doesn't go across town to go grocery shopping. He buys groceries near his house. He does his dry cleaning near his house. He stays near his house. So to a program, the lines of code don't jump far and back. They usually progress in a certain order. There's hardware support that's needed for demand paging. We need the page table with the valid and invalid bit. In other words, we want hardware to detect that the bit is invalid. We don't have software that detects that. We have hardware that detects that. We need secondary memory. Obviously, we need a hard disk with designated swap space. What do we mean by swap space? It's space that we can swap programs in and out of. We need instruction restart capability. We need to be able to take an instruction and run it again. A problem with instruction restart. A simple store word can be restarted if the store location is not in memory. Right? A simple store word can be restarted if the store location is not in memory. Because I want to store something I want to store a register to this place in memory. That memory is not in, so I'll bring it in and then I'll restart and copy it. That's fine. Consider an instruction that could access several different locations. For example, a block move. Let's say I have some kind of instruction that says move everything from address 0 to 50 to address 25 to 75. You see what I'm saying? if they're, notice it's overlapping. I didn't say, if it was just take everything from 0 to 50 and move it to 100 to 150. So that's fine, but what if it's overlapping? What problem can arise?
Could you like lose data? Like in the other location?
Well, what is written here? Some of the source data may have been overwritten when the page fault occurs.
It's not the other. Yeah, wait, why
Copying over the source.
Yeah, you're copying over it, so I would have thought you would lose stuff in the destination if you don't check.
Well, look, the arrow actually points from here to here.
Which was where?
I'm copying from here to here. Well, either way, this is problematic because I may write this piece to here, and then I've lost what was here. Notice the page fault only occurred when I got to a certain point. And now if I restart it, I'm going to restart it, but it's going to be with data that's already been changed. I was trying to change data, but I was very careful, and I copied it first, and then I changed it. But now it says restart the whole instruction. But the instruction is this large command, copy all this data to there. So I'm going to restart that whole process again, and now the data I already copied some data. What would I have to do? I'd have to unwind what I've already done. I have to remove all the changes that I've made.
That's Control Z.
To do that, but I wouldn't. One solution is to determine if a page fault if a page fault will occur before even starting the operation, but this is costly. So in other words, I could say, well, this command in particular is going to cause a page fault because it's asking for a page I don't have. It's going to be asking, as it runs. There are other problems that need to be solved as well. So there are certain problems with instruction restart. So here are the steps in handling a page fault, accessing an invalid page. So let's see if we can understand this. 1, we have a command that says load memory, load something into memory. If you remember the load command. Reference 1. I go to the page table. It tells me what? Invalid. So it generates a trap or an interrupt. I go to the operating system. The operating system says, oh, you had an interrupt. I'm happy to help you. Page is on the backing store. He figures out that the page is in the backing store. He copies the page and brings it into physical memory. He must find a free frame in memory. Let's assume that he finds a free frame, places it in the free frame. Now he goes and resets the table, he changes the table to be valid, and he goes back and restarts this load memory. And now says, try this load memory again.
Again, the cylinder on the right is the virtual memory, correct?
It's the hard drive.
Yeah.
Yeah.
Thank you.
Here I wrote out in great detail all the steps.
That's a lot of stuff.
So it's like this is the simple version, but it's the same thing. Trap to the operating system. Save, first of all, there's a trap to the operating system. That's this trap here, and we found it's invalid. Save the user registers in process state. Well, we're going to let the operating system run. He's got to have access to registers, so we've got to copy out, save the user registers in process state, because the whole process is now frozen. Determine that the interrupt was a page fault. Figure out why did we get here? Why did the operating system get interrupted? It was a page fault. Check that the page reference was legal. So he has to check, is this a page that he's assigned? And determine the location of the page on the disk. Figure out where it is on the disk. Issue a read from the disk to a free frame. So we're going to read that page. We're going to ask the DMA to copy a whole page to a free location. I actually don't even write here how we find the free location, but we have to find the free location. Wait in a queue for this device until the read request is serviced. We've got to wait for the copying to take place. Wait for the device seek or latency time. Begin the transfer of the page to the free frame. While waiting, allocate the CPU to some other process, right? While we're copying this page, we don't want to just do nothing, so we'll give some other process the chance to use the CPU. Receive an interrupt from the disk I/O subsystem. I/O complete. We got to be notified now that they finished copying. Save the registers and process state for the other user. So if we're going to interrupt the other user, we've got to save his registers. Determine that the interrupt was in fact from the disk. Correct the page table and other tables to show the page now in memory, because maybe it could be a shared page. So we may have to change other tables. Wait for the CPU to be allocated to this process again. Restore the user register process state and new page table, and then resume the interrupted instruction. So that should all be quite logical. Let me just make step by step all the things that have to happen. I'm sure it's missing something. Okay. Remember we talked about epsilon? We had a very similar concept. We had a hit rate. What was that a hit rate for?
We're finding it in page two.
In the TLB,
TLB.
transfer look-aside buffer. In the TLB, we had an epsilon hit rate. Now we're going to have a different thing called P, which is the page fault rate. The other was epsilon was the hit rate for the TLB. This is the fault rate for the page at all, right? Whether it's in memory at all. So if P is equal to 0, then there's no page faults. If P is equal to 1, then every reference is a fault. So it's going to be a percent. What is our percentage fault rate? So EAT equals it equals 1 minus P would be the hit rate. So it's the hit rate times how much time it takes to get the memory, plus the fault rate times whatever the fault overhead is, plus the swapping page out and swap page in. What does that mean?
We need to load the.
From a hard drive.
We need to.
Right, we need to wait for the DMA to copy it. When do we have a swap out? Why do we have a swap
Oh,
out?
in case
When
the,
memory's full.
yeah, the pages are full. I mean, we don't have any.
We didn't, so we had to swap somebody out, okay.
Yeah.
But if we had a free page, would we have this swap out here?
No,
No.
I don't think so.
well, unless the program finished, but that's also relevant.
Also, wait a second, no, wait a second. Oh, you're saying swap out of another program?
Yeah.
It could be also swap out, right, it could be swap out of another program, but it could also be that it's full. But we don't need to swap out. Can you imagine a case like, when do we need to swap out and when do we don't need to swap out? We actually talked about this in computer architecture with the dirty bit.
Mhm.
We don't really need to do a page swap out
If it's not changed.
if it hasn't been changed. It's always, because remember at this picture here? Look at this, where is this picture here? Look, even though A is in memory, it's also on the disk.
So it also.
I don't need to, let's say this would be all full, I need to swap out A. I don't need to swap out A, he's already there.
So he also has the dirty bits, all of them, to see if.
It's gonna have to be in a dirty bit. Yeah, why would I want to swap it out if it hasn't changed? So this is like only a ratio also. There should be a ratio of how often I need to swap it out. And then swap it in, and then restart overhead. How much it takes me to restart. That's kind of like a summary of these 12 steps here.
Yeah.
You got the basic idea, but here's an example. Memory access time is. Yeah, I have to, okay, there was an example in the lab that I changed, and now I realize I can change it again. But anyway, okay, memory access time equals 20 nanoseconds. 200 nanoseconds, sorry. 200 nanoseconds. What is a nanosecond?
Oh, it's millions?
Millionth of a second.
No, that's
a
microsecond. A
microsecond
is a
millionth of a
second.
A billion?
A billionth.
That's a lot.
It's a billionth of a
Actually,
second.
That's a
It's not a lot. It's very little. It's very little.
Oh, alright.
200 nanoseconds is less than a millionth of a second, right? It's a
1/5.
fifth of a millionth of a second. Average page fault service time is 8 milliseconds, so we're screwing around here with time, because now we're talking milliseconds. How many nanoseconds is 8 milliseconds? What's a millisecond?
1,000. So it's a
Thousands of a second, so how many nanoseconds is 8 milliseconds?
A million.
No, it's not.
1 million.
well,
Oh,
okay,
eight
what's the
million,
question?
8 million.
What's the question?
The question is, it says here 8 milliseconds, how many nanoseconds is that?
8 million.
8 million. 8 million, nanoseconds are really small, so you can get a lot of them into 8 milliseconds. 8 million of them. So what is the average? EAT, what is it? Access time,
Access time.
E, what does E stand for? Effective, effective access time. So what is the effective access time? It's the hit rate, that's the hit rate, times 200, that's how long it takes a memory access,
Mhm.
plus the miss rate,
Those hit rate.
P is the miss rate.
Ah,
Average page fault service time is 8 milliseconds. So that's it, we're done. Right? That's it. That's the equation. But we can expand, we can change this, since this is in nanoseconds, change this to nanoseconds also, so it becomes 8 million. And then we can multiply this stuff out and say, well, this is 200, 1 times 200. This is negative 200p, and this is plus 8 million p, so it becomes about 8 million p. So it's 200 plus 8 million p. What does that tell us? It tells us that the estimated, no, effective access time, effective access time is directly proportional to P. As P goes up, EAT goes up. What is P? Hit rate. I mean, the miss rate. It makes sense. It's directly proportional to the miss rate. As the miss rate, as you get more and more misses, it's going to get slower and slower. If one access out of 1,000 causes a page fault, so that means if our one access of 1,000, that means if our P is 0.001, then it's 200 plus what?
200 plus.
It's 200.
7,999.
Well, basically 1,000, just drop off a decimal point, and you get 7,999, which is basically 8. So it becomes
10.
8
No, no,
plus 200.
8,200.
8,000 plus 200, so 8.2 microseconds. What is a microsecond?
A million.
Second.
That's a million of a second.
Pretty good.
So this is so if one axis out of 1,000 is a page fault, just sounds great. How slow will it be? 8.2 microseconds. But wait a second, if we had no misses at all, what would it be?
200.
200 nanoseconds. So what's the ratio between 200 nanoseconds and 8,000 nanoseconds? This is 8,200 nanoseconds. 40. This is 200 nanoseconds. They really screwing around because they changed this. They changed this in a very mean way into microseconds. If they left it as nanoseconds, it would be easy to understand. This is 8,200 nanoseconds. 8,200 nanoseconds versus 200 nanoseconds. Well, if you take 200 multiplied by 40, you get 8,000. So it's a factor of 40. Now we're asking the question this way. What if we want the performance degradation to be less than 10%? We don't want it to be 40 times. We want it to be only 10% worse. What's 10% of this? What would it be if it's 10%?
20 nanoseconds.
What?
20 nanoseconds.
Will be 220 nanoseconds. 220 nanoseconds will be a 20%, a 10% increase. So instead of it being a 40 times increase, you want it to only be a 0.1% increase, 0.1 increase. So we have to say like this. So we want performance equation, so that means we want it to be 220. We want that to be greater than the 200 times the plus the p times 8 million nanoseconds. So we divide, what do we do here? We subtract 200 from both sides. Fine, and get rid of the 200. So it's 20. So we have to have a p of very small. I can't even say that. Whatever that is.
0.0000002.
Yeah, very small. One page fault every 400,000 memory accesses.
We're not
That's
gonna
what we
get
would
that.
want, and that would still cause us a 10% increase.
We're not gonna get that.
Just saying, we don't want to have a lot of page faults. So therefore, this motivates us what? That is the motivation to what?
No.
To come up with a good algorithm for keeping the right number of pages in memory. It becomes very important for us to have exactly the right amount of pages and the right pages particularly, which, the right pages should be in memory all the time. So demand paging options. One option is copy the entire process image to swap space at process load time. So we'll copy it into, what do we mean by swap space? A place in the disk that's meant for virtual programs. Then page in and out of swap space, which is faster because of how the swap space is designed. Oh, you understand what's going on here? Instead of just saying, up to now, we didn't really discuss this. We just said the program's on disk. But we did have a picture that sort of was misleading over here. Remember we saw the picture? We saw a picture. So a picture, I didn't really emphasize it because I didn't want to talk about it yet. See, it says this shared library, well, oh, wait, is that, no, that's not the picture one. Oh, I thought that was a picture, swap space. That was swap space. Maybe it wasn't a picture, maybe we just said it.
You slow her down.
Is it not?
All right, never mind, there wasn't a picture. We may have said it though. Anyway. So what we're gonna do is like this. One idea is that we'll have a special space, when you actually install Windows, sometimes if you do like the detail, if you just say yes to everything and just let it do what it wants, default to everything, then Windows will do what it does. But you can also go into advanced mode when you're installing Windows, and then it asks you a bunch of questions. And one of the questions could be, how big of a swap space do you want? And you can say, I want a swap space of this size, or
Swap space is something in the hardware?
no. You define an area of the disk as swap space.
So there's no hardware optimization, it's even faster.
There may be the operating system optimization, maybe the way the operating system relates to it. I don't know much about it, but there is an area that you can define as swap space. And so what it's saying is like this: when you want to run your program, first thing you do is you make a copy of your program into the swap space. So now your program actually exists twice on the hard drive, twice on the hard drive. Once where you stored it, and once in swap space. And this swap space is like is just an area of the disk that'll be accessed in a better way. The other idea is demand paging, demand page in from program binary on disk, but discard rather than paging out when freeing frame, because the page is never modified. So that's what I said to you. If there's no dirty bit, we'll just discard, used in Solaris. So in other words, when the page I want to be swapped out, we will just throw it away. I mean, I don't see why I can't do that also if I have swap space.
Yeah.
Okay. There's also a concept called copy on write. What is copy on write? It allows both the parent and child processes to initially share the same page's memory. So when I do a fork and I create a new process. Initially, as long as the two processes don't change anything, don't change any variables. Then they don't need to be separate in memory. And the idea of copy on write is that the operating system will notice as soon as one of the programs, either the father or the child, changes some shared data, some data that not shared, but some data that is currently shared but shouldn't be shared. While he's changing it, I better make now I better make a page for him. So it's sort of like I let these two programs use the same memory until I can't anymore. Because why can't I anymore? Because somebody did some writing.
And we're assuming that mutual exclusion will cause problem. You know, like, if a parent and a child.
Well, that's the thing. Oh, if they're both right at the same time.
Right, that's not an issue here because we just assume the system doesn't work, doesn't have that issue.
So. But it's only the child. I guess
Sharing
if
is
there's
the
only
problem.
two processes, then you only have to copy on the child. No, you don't.
That's an interesting question. It's an interesting question. You're saying, what if the father and the child, and you have two, let's say you actually have two processes running. And the father's on one process and the other, and the child's on the other process. And they both at the exact same moment write to the same data. Then I have to create new data for the child, really. The father will keep the same one.
Well, like, let's say the
So
child.
as soon as the child starts to write, we won't let him write. We'll first create memory for him. If he does a write command, we'll detect that and not let him write. That's the point.
Got it, okay.
So this COW or cow
Cow.
allows more efficient process creation as only modified pages are copied. We may never copy certain pages because if they're never modified. In general, free pages are allocated from a pool of zero fill on demand pages. So in other words, we have some pages. What do you mean by zero fill on demand? Maybe they have zeros in them?
Why do you need zero?
Why zero out a page before allocating? Question. Because he may go beyond the end of the page. He may go on the page. Right, let's say when I allocate a page, I allocate a whole page, but he only maybe needs half a page. So he'll have data. He'll have non-zero data in the part that he's not using. Maybe he will use it, maybe he'll run beyond it. I'm not sure if it's necessary. There's something called a V fork, which is a variation of fork. System call, which has parents suspend and child uses address space of parent, but without copy on write. So it's a virtual fork. The parent suspends himself, and the child now uses the space of the parent without even having copy on write. So the child will affect the parent. It's a virtual fork. It's not really a fork. What is the advantage of it? When would you use it? Let's say the child, a very simple case for instance. Let's say I have this exec command, where the whole reason I created the child was just to run an exec. But he doesn't need to change any data, he just needs to run a program. He just needs to right, he's running a different program. Well, when he runs that program, isn't he gonna have to bring a new page to that program? Yeah. He'll bring in new pages. When he eventually dies, then the parent will be activated. So it enables me to run a child without any overhead immediately. And he can then execute another program. And then when the parent comes back, he doesn't care about those pages that child is using because he's no longer using them. He's not going to use those pages. I think it could be very useful for the exec.
We spoke about this before.
Modification right here. Modifications made by child will be visible to the parent, that's the problem.
How-
Designed to have the child call exec, exactly what I said.
How's the
Very
parent able-
efficient, used in shell implementations.
How's the parent able to see everything if he suspended himself? Did he just unsuspend?
No, I'm saying when the father would come back, any changes that would be made by the child would theoretically affect it, but let's say the parent is like this, the parent. You know. Wait a second. Here's the father, and he does his int a equals 7. He does whatever he does, and then he does virtual fork. Equals 0. If virtual fork equals 0, then exec. I don't know, ls. He runs the ls command. And then else. I don't know, cout. A. Okay, so. If this child in here would have changed A. Then when I printed A, the father would see it, would get it. I would get the change. In fact, I would have no race condition here. Because it's not really, the father is immediately suspended when I do a virtual fork. Now if he would have changed A over here, this A would be different, because it's actually the same. But what I did was only do exec. And exec just says go run another program called ls. Well, ls is somewhere else on disk, and the pages for it are going to be totally different pages than the pages for the actual program here. So the child will go run that. Now, when he finishes, he'll die, but that won't kill the father. Because because he is actually a child. So we sort of get the best of both worlds. You could say, why bother creating a fork? Why do we want to create a fork to do exec? Because if we don't do a fork and we do an exec, then whoever did the exec finishes the exec, the program ends. And I never get back to this line of cout A. So I have to do a fork, but I'm going to do a virtual fork so that I don't have to waste time creating a new process. Very efficient. Before process 1 modifies page C. What do we have here? After process 1 modifies page C. I was just showing you cow. This is cow. In other words, we have process 1 and process 2, and they're using A, B, and C. And before there's any modifications, they're just using them, they're running the exact same thing. And now, the minute that process 1 changed C, he's going to use his version of C.
Will process 2 ever get a copy, the same copy? Meaning like if they're children of the same parents, like in the feed.
Well, you kind of asked, what if both of them change C at the same time? Then maybe there'll be 2 copies of C, and the original C will get unused.
Oh, yeah, I'm just asking in general, like, does it, like, I thought process 2 shares the new copy. Am I wrong?
No, you're wrong. No, we made a fork. This is not virtual. This is real.
Oh, okay.
This is a regular fork with cow.
Thank you.
Okay, what happens if there are no free frames? We have been assuming we can always load a page from the disk into memory. What if all the memory is in use by process pages? In other words, all the memory is being used by pages for processes, or in use by the kernel. A bad solution is to kill one process. We could just say kill some process, and then you have some space. Another solution is to swap out a process, take a whole process and put them on the disk, and then I'll have space. Consider a third solution, page replacement. Find some page in memory, but not in use, either by myself or by another process. Page it out. Copy the page to swap. To swap, because interesting. It sounds like from these slides that when you use swap, you don't leave it in the swap space when you put it back. You don't have 3 copies of it at any time. That's what we're saying here. You don't have 3 copies. It's true that the original is on the disk, but then we made a copy into the swap space. And then when we bring it from the swap space into memory, we remove it from swap space. We don't leave it there. So when we take it out, we do have to copy it back to swap space.
Yeah.
So therefore, if we go back to that slide over here. Where we talked about swapping a page out and swapping a page in, we do have to do that, always. Even if it's clean. Even if it's clean, we're gonna swap it out, because we don't care that it's clean, we always want a copy to be in the swap space so we can get it faster. Next time.
So what was it talking about, like the optimizations page, like this one?
Yeah,
previous
swap
page.
is, what is
Uh,
it?
Previous, go back to one more, this one, no, there at the bottom, when it says, isn't this our solution? The bottom one.
We're assuming the top one. This is the way I was understanding it.
Yeah.
This is the way I was
This-
explaining it
this
before.
slide is wrong? Or no?
No, there's two different ways, we're assuming the first one.
Oh, so they are exclusive, like you can't have both a swap space and the dirty bit.
Yeah.
Okay.
They are exclusive. They're exclusive bits. The dirty bit is the way I was understanding it, the way I would think to do it. But that's without a swap space.
Mhm.
When you have swap space, you want to always keep it in swap space. Okay. So consider a third solution, find some page in memory, copy the page, it's really the order of these slides is a little bit mixed up. Because it would have been nice to know this before, and then you would understand what is it. So copy the page to swap. Mark the frame as invalid. And add the frame to the free frame list. Right, and now for this guy, though, for the process that you swapped out his page, you have to mark it as invalid.
Yeah.
And you have to put it onto the swap space. Now you can load the new page into the free frame. Performance, we want an algorithm which will result in a minimum number of page faults. We don't want a lot of page faults, we want a few. Some pages may be brought into memory several times. You may swap it out and swap it back in. If the page has not been written to while it was in memory, no need to copy it back to the disk.
Right.
Or swap space on the disk.
We just.
We just said you did. Yeah. Well, I think it depends on your algorithm, depends on what you're doing.
No, it doesn't say we need to, where does it say that we need to copy it every single time? Like even if it isn't. modified?
Here,
Oh,
the
no,
we just did.
oh, yeah.
here, it says swap page out, swap
Also,
page in.
oh,
I
we
just
just
thought
did.
that was like an option.
And also what?
Also, the thing that we just did, this one is copy the page to swap.
Right,
Oh, yeah.
now he's saying, well, don't copy the swap,
Or no, we need
maybe,
to-
if it has not been written. If a page has not been written to while memory. No need to copy it back to the disk, you see, I think the disk is actually the correct. And in parentheses or swap space on the disk, that depends. Use modified or dirty bit to reduce overhead of page transfers, only modified pages are written to disk. Page replacement completes separation, here's an important point, page replacement completes separation between logical and physical memory. A large virtual memory can be provided on a smaller physical memory. We have a session after Mincha, right?
Yeah,
Yeah,
it's 5:05.
Well,
Until 5:05.
so 5:05.
Yeah.
What is our time now?
3:56.
Two. Okay. Basic page replacement, find the location of the desired page on the disk. Find a free frame, you have to find the page on the disk, then you find a free frame. If there is a free frame, use it. If there's no free frame. Use a page replacement algorithm to select a victim frame. A frame that you're going to remove. Write the victim frame to the disk if dirty. Bring the desired page into the newly free frame, Update the page and frame tables. Continue the process by restarting the instruction that caused the trap. Note potentially two page transfers for every page fault. Why? 2 page transfers for every page fault?
So because you swap it in and out.
If there is no free frame. Select the victim and write the victim. Now bring the desired page. That's all they mean. Now there's 2 page transfers, right, because that's what we said before, it's 5 slides ago. That we said there's 2. Increasing EAT, not really, because we already put it, we already had it there. Okay. Yeah, it's a little bit misaligned in some of this information. I guess I really need to edit even more. So here's a picture of what we just said, frame. We say 0 is invalid, F is valid. Do we want F? We're fine. So where's 1? Oh, swap, that's over here. Swap out victim page. Take the victim and put him onto disk. Swap desired page in. No, first change the invalid. Change to invalid. F is no longer valid, he's invalid. Now, bring him in, I don't see why we have to change it at that point. Swap desired page in, and now reset page table for new page. This is a little bit confusing diagram. But the basic idea is that the victim goes out, that this page is removed, a new page is put in that place, and the page table is changed appropriately. All right, we'll stop here, and then we'll talk about the algorithms and examples.
Question, would I be able to get homework 5 open here?
Oh, wait a second, stop share.
I have one, I
Okay.
get 5.
2 types of algorithms are needed. Right, in general, we need 2 types of algorithms. We need a frame allocation algorithm to choose which frame. How many frames to give to each process in the beginning. Let's say,
Is that an algorithm? It's like you just choose.
right,
It's like,
Range.
it's a one-time thing.
I think it's more like you can have.
right, but we need to figure out, we need to have some kind of estimate. Bigger programs maybe get more frames.
Like,
Smaller
you might have a
programs get
program that
less
needs
frames. We need
3.
some kind of algorithm.
Okay, I guess.
Page replacement algorithm, which frames to replace, choosing a victim. Want the lowest page fault rate on both first access and re-access. Okay, evaluate, in other words, we want to have pages that we might need again. Evaluate algorithm by running it on a particular string of memory references, a benchmark reference string. And computing the number of page faults on that string. In other words, if we have different algorithms, we can say, well, what if we have a theoretically, ask for this page and this page and this page and this page, what would be the number of page faults? And what would another algorithm? So if we want to figure out the best algorithm, maybe we should do that. We should use different benchmarks. It could be that one benchmark program will tell us that a certain algorithm is better, and a different program will tell us that a different algorithm is better, depending on how the pages are arranged. If one, for example, uses a lot of times the same page, or they have different characteristics of page use. Evaluate algorithm running on a particular reference string. All right, string is just page numbers, not full addresses, because we don't care which address in the page he accessed. If he either he needs this page or he needs a different page. Which page does he need? Repeat access to the same page does not cause a page fault, obviously. Yes.
Is this just like the same type of thing that we look for when caching? Like which cache things to swap
Yes,
out?
it's the same basic idea. Cache, we want to have the cache, we want to cache the best stuff. Here also, we want to cache the best stuff. In all our examples, the reference string will be the following: 7, 0, 1, 2, 0, etc. Okay, so graph the page faults versus the number of frames. So this is the way you would expect it to look. This is the graph, the way you expect it to look, which is that if I have only one frame, I'll have a lot of page faults. I'll have 14 or 15 page faults. If I have, in fact, actually look at this example. In this example, I never use the same page one after the other. Every time it's a different page. So that means if I only had one page, if there's 15 references here, I'd have 15 page faults. And as the number of pages goes up, number of frames that I have allocated, I'll get to a certain point. Where I'll have like 5 page faults, let's say. And will it continue? In other words, at a certain point, I'll have them all in the page, all in memory,
When you have 15, you have 0.
even before that. No, I want a 0, I'll still have one page fault, I'll still have a page fault for everything. In other words,
So we're assuming that it starts off with nothing.
I'll never get below 4, the point is here, I'll never get below 4,
Because
as
that's
the number of frames increases, I'm not gonna get below 4 because. I use 4, I use 0, 7, 0, 1, and 2, and 3, actually, I use 5, in this particular list, I use 5. So I can never get below 5.
So we're assuming that
That's what
the first one is always a page fault, first appearance of it, if nothing starts
Yeah.
out memory.
Assuming that it's pure, assuming that it's pure demand page. Okay, let's take a real example here, or not a real example, but a more specific example, where we have 3 frames. And now we have the same reference string. 3 pages can be memorized at a time per process, well, for this process. So as our 7 comes in, he goes into page frame 1. 0 goes into page 2, and 1 goes to page 1. Then we have for 2 will go, well, we're assuming that we're gonna just use like first in, first out. That's what it says here, first in FIFO. So that means that the first one in was 7, so he's the first one out, so we'll put in 2 there. Then we'll put 3 where 0 was. And gosh darn it, we took out 0, but the next one we need is 0 again. Would have been nice if we knew the future, but we don't know the future. In our algorithm, we don't know the future. And so we took out 0 because he was the first one in, next first one in. And now we put in 3. And now 0 comes, we put out 1. And we keep going, following this order. Sometimes we find that we don't have page fault. For example, after
I think we always have page.
pretty much, yeah, it's a pretty bad.
It says 15 page faults, I think.
So 15 page fault, that's a lot. Okay, we can vary by reference. By reference string, consider this string 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So there's something, right, it can vary. If we have 1, 2, 3, then 4 would go here, and then 1 would go here, but
2 would be fine.
2,
Sorry,
no, it would,
I mean, 2 would be fine, yeah.
2 would still be kicked out,
Yeah, then 5.
then 5, then 1 would be okay. When we get to this 1 over here, it's still in from over there. And when we get to this 2 over here, it's still in from over here.
Yeah.
Do I have an example of validities? Yeah, oh, so now look at this reference string. So how to track pages, ages of pages? Well, we could just use a FIFO. That's not really age, but it's, why is it not age? Because it could be that my list was, let's say like this, 7017. 7, then 2, 0. So I would still kick out 7 when 2 came along, because he's most recently used, but he was the first one in.
Yeah.
You see what I'm saying? FIFO just told me who got into the list first. I kick him out first, even if he was recently used. So we could not track age, we could just do the FIFO. Think about this reference string. Look at this. How many page faults do we have here? Oh, this is our same example?
Maybe. Yeah, I think so.
20304, yeah. So this is our same example, and we see, I guess we're just doing it clearly now. 7, 0. This is the way you should do it. 1. Then 2 comes in. Then 0 is requested.
And there's no issue.
What?
There's no issue.
And there's no page fault, because he's there. So that's why we have this blank line here. The idea is that we didn't do a page fault. And then 3 comes, oh, but he's not there, so we kick out 0, even though it was just referenced. We don't care about reference, we care about order of entry. So 3 goes in, then 0 comes again, and we have to kick out 1. Etc. etc. You see how many page faults, just count the blue boxes. 1, 2, 3, 4, 5, 6, 7, 8, 15, 11, 12, 13, 14, 15. Okay. Now-
That weren't faults.
If we go back, let's go back to this list. Here, let's do some work. This will be a good exercise and also teach us something. let's say it was instead of 3, 4. What would you expect? More page faults or fewer page faults? You would expect fewer, because we saw that graph. If we have a lot of frames, then eventually everything's in memory. So let's try it. 7. We're gonna still, I gotta do a lot of work here. 7, 7, 0. Seven, 0, 1.
7012.
Up. 7, 0, 1, 2. Now we have 0. And he causes nothing. Then we have. Then we have 3 comes along and we have to kick somebody out. Who are we gonna kick out? 7. So it's gonna become 3, 0, 1, 2. That's for 3. Now 0 comes along. We don't do anything. Let's put that here. And 4 comes along. Who do we kick out?
4 zeros.
0. So 3, 4, 1, 2. Then 2 comes along. Actually, it looks like it's doing better, isn't it?
It is.
Wait, 4 was here. 2 came along, we had a hit. 3, we also have a hit. Let's do that. Let's draw that. Wait a second. 4 came along, 2 came along, is here. 3 came along, is here. And now what? 0 comes along. Oh, 0 is going to be a miss, right? Let me change my pen. Or actually, I can go like this. 0 comes along, who are we going to kick out?
1.
1. So it's going to be 3, 4, 0, 2. Right? That's this 0 here. Now 3 comes along.
We're fine.
And we're fine. And 2 comes along, we're fine. Now 1 comes along.
3401.
Oh, wait a second. Maybe I picked the wrong number. Yeah, we're not proving much here with this, but whatever. Okay, 4 out of there. Okay, what do we have?
3401.
Sorry, I lost track.
1 comes along.
This comes along 1, right? And we kick out
2.
y, because 0 just came in. So 1 comes along, so it'll become 1, 0, 4, 3. That's 1. Then 2 comes along. And
Not 3.
we have to kick out 3. So it's 2, 4, 0, 1. Then 0 comes along, we're okay. And 1 comes along and we're okay. Looks pretty similar. Now what? 7 comes along. Who do we kick out? 4. 2, 7, 0, 1. Then 0 and 1 come along and we're okay. So how many page faults do we have? 10, it went down. Well, that's not an anomaly. That makes sense. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now look at this picture here. That's if there's 4. If there's 4, there's 10 page faults. That's what this chart says. See, 4 is 10. But wait a second, if there were 3 frames, it says only 9.
We have 15. That's not 9.
That's not 9? Is there a mistake here?
I think it's just talking about.
Okay.
Random string.
What?
I think it's just talking about a random case, not a.
Well, no, this, I once worked it out that this is actually right. Look, it's exactly right. 10. We just did it. It's 10. I don't know. If it's 5, the point is,
With 1, it's definitely not 12. So with 1, it goes 20, because the string is 20 long.
yeah. Okay, so I don't know. I remember this as being correct. Maybe the string was different. Okay. In any case, the idea of the Balades, you should know what Balades anomaly is. The idea is that it's not necessarily gonna look, this curve is not necessarily accurate. It could be that at a certain, for a certain string, having 3 just happens to work out better than 4. Because by 4 means you replace different ones, and then, of course, you only have Balades anomaly in FIFA. If I would somehow, there's something called the optimal algorithm. The optimal algorithm is where I somehow know the future, and I always choose the perfect one to remove. In such an algorithm, I would never have an anomaly. So optimal algorithm, replace page that will not be used for the longest period of time. 9 is optimal for the example on the next slide. I guess for our example. Assuming 3 frames. How do you know this? You can't read the future. So why do we have it? Why do we even talk about it? The optimal is only talked about as a way of gauging other algorithms. How close is it to the optimal? Here's the optimal. Well, we're obviously going to put in 7, 0, and 1 as they come. But then 2 comes along. We look ahead and we see we're going to need 0 and 3. Well, so
Which one is used in the longest period? 7 isn't used for a long time, so you know.
Exactly. 7 isn't used for a long time, so we kick it out. And then 0 comes and he's there. 3 comes and we have to put him in. We're going to take out 1 because 1 is used until all the way over here, but 2 and 0 are both used before that. So we're going to kick out 1 when 3 comes. And then 0 is there. 4 we have to kick out. We'll kick out 0 because 2 and 3 are about to be used. Truth, it doesn't really matter here. Well, it does, consider there to again. So anyway, we kick out 0, put in 4, and now 2 and 3 don't require anything. Now 0 comes, we kick out 4 again because he's not going to use it all for the rest of the time. So we put in 0, and now 2 and 3 are used, and now 1, well, we see that 3 is no longer going to be used, so we can kick out him and put in 1. And then we have 2, 0, 1. And then 7 is again used, so we kick out 2 because he's not going to be used again, but 0 and 1 are. So you see that the optimal is 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's only if we can look somehow ahead. So the least recently used is kind of a better idea. On the theory that the recent past is a predictor of the close future. Use the past knowledge rather than future. We can't know future, we can know past. Replace page that has not been used in the most amount of time. Associate time of last use with each page. We're gonna have some kind of hardware stamp, like the hardware, and then you're gonna keep track on each page when it was used. And every time it's used, we change that date. Which is going to be costly, but we'll have hardware especially designed for it. That would be the ideal thing, have an actual date, the exact date, like the number of seconds since 1970.
Yeah.
And that number will change, and then we'll know exactly when it was used. And then we can compare 2 different ones, and we can when we have to remove somebody, we go through all of them and find the oldest. So here's our reference string, and this is the result you would get if you use the least recently used algorithm. Why? Well, 701 is obvious. Okay, now who are we going to remove? Well, 7. He's still least recently used. 0 comes along and we use him. So now when 3 comes along, we're not going to remove 0, which we would have done if it was free FIFO. But we're going to remove 1 because it hasn't been used for a while. So 3 goes in. And that's actually good because now we're about to use 0. We'll use them the next time. Now 4 comes along, who are we going to kick out? Well, the last 2 we used were 0 and 3, as you can see over here. So we're going to kick out 2. Now 2, unfortunately, wait a second, we kicked out who? We kicked out 2,
Yeah.
But unfortunately we're using him. But who are we going to get rid of? Well, we're not going to get rid of 0 and 4, we're going to get rid of 3. But 3 is the next one we're about to use, but we don't know that. Now we actually want to use 0, anyway, we're getting all screwed up here. But it could work out in a good way. 0 comes and we put 0 in. Now 3 comes and we kick out. 3's already there. And 2 is there. But 1 comes and we kick out 0 because 2 and 3 have just been used, but 0 has been used long, a little further away. So we kick out 0. And then 2, we get to use him, we have him, but now we need 0, so we kick out 1, no, we kick out 3, because 3 has been used till all the way here. We've just been using 2 and 1 and 0. So we kick out 3 and put in 0 here, etc. So how does this come out? 1, 2, 3, 1, 2, 3. That's
Well-
not, that's 6, 9,
Well,
10,
well,
11,
well,
12. 12, okay. Close to the optimal, close, is it somewhat close to the optimal? Better than 15. All right, how are we actually going to implement the least recently used? That's gonna be our topic actually now. Because keeping that stamp of the date is kind of a slow way of doing it. It takes up a lot of data. So one is a counter implementation. Every page entry has a counter. Every time a page is referenced through this entry, copy the clock into the counter. I mean, okay, it's fine. So the counter is just I don't know why we call it a counter, it's just the clock. Every time a page is referenced through the current entry, in other words, a current memory request for a particular address happens to be on this page, then copy the counter into the page. When a page needs to be looked, and there's not a counter simple upping. Why don't we just have a simple counter that goes 1, 2, 3 every time it's accessed? That would cause a certain problem. What problem would that cause?
The critical section problem construction. That was a joke.
What?
That was a joke.
What problem would happen if you just up the counter every time you used it? Then you keep track. Then what would that be? That would be how often it's used.
Yeah.
You could have a problem with that though, because you could have a page that was used millions of times, but hasn't been used for a long time.
Yeah.
So it'll be stuck in our system. We'll never get rid of it because it's been used so much. We'll never get anybody who uses more than him, but he hasn't been used in ages. So we'll have a problem of like of a useless page in memory. So that's not a good
We should
system.
combine the two of them. We should have a ranking for how many, it's the counter and ranking for its time. And then we add
That would be the best, right? If it's also recently used, then you'd have to think about how to weight those two things. Yeah, that would be a good way. But what if it was used many, many times and hasn't been used for a long time, but it was used right now, it just happened to be used.
And refreshes for a
Right,
while.
and it refreshes. Anyway, fine. Basically, you could have a counter system where you just up by 1 and then have a Udafka when it gets too big, you remove it.
Mhm.
Just to refresh it. Anyway, copy the clock. The clock makes a lot of sense. When a page needs to be changed, look at the counters to find the smallest value, because the clock is just a number. And the higher the number is, the more recent. So the smaller the number is, the older, we get rid of the older. Search through the table is needed. Well, that's gonna be slow. We're gonna have to go through a table, we have to search all of the dates, and we have no idea which one that we're gonna, to go through them all. Stack implementation. So another idea. Keep a stack of page numbers in a doubly linked form, page reference. Move it to the top. Anytime page is referenced, put it to the top. You understand what I'm saying? You have a stack, and anytime that page is referenced, so then pull it out and put it to the top. And who do I remove? The lowest one on the stack.
Yeah.
And I keep on putting, as I reference them, I keep shuffling.
But you still have to search through the table.
So it says, no, you don't have to search, you know always to go to the bottom, you have a pointer to the
How do you
head,
find the one that you're moving.
you have a pointer to the head, you have a pointer to the tail.
How do you find the one that you're moving to the top? You're given some page number that's being accessed, you have to move it to the top somehow, right?
Right.
So doesn't that require searching through the stack?
Yeah, it would require searching through the stack till you found it, yeah.
Ah.
Unless yes. I don't know why it says requires 6 pointers to be changed, exactly 6, but we have a head.
You got that head, tail, you got the
The
further
further-
link between the head and tail, and the 2 links between the head and the second.
Okay, if it's forward and backward pointing. But it doesn't need to be forward and backward pointing, could be
It's
just,
a doubly linked, doubly linked.
oh, it says doubly linked?
Double.
If it's doubly linked, okay, so then it's 6, yeah. But it doesn't have to be doubly linked, it could be singly linked. Why would you want to go back and forth? You could just have a head and a tail and then a single link. Okay, but each update is more expensive, right? No search for replacement. Well, because we have a pointer to the tail, but you're right, we do have a search for well, that's what it means, update is expensive. Updated fence means we have to find where it is and move it. So. Now we say like this, least recently used and optimal. Are cases of stack algorithms that don't have Balinese anomaly. In other words, both of those, the optimal for sure doesn't have Balinese anomaly, and also the stack one won't. What about the timed one?
The counter one?
I don't think the time one would have it either. Yeah, the counter, with the counter and time, the date.
The dates? Oh, but probably not,
What's the
Exactly.
anomaly again?
It should be not, Balinese anomaly is that sometimes when you, in FIFO, if you add more. Frames, you could actually make things worse. It's possible, but unlikely unless in fewer scenarios will make things worse, but in some scenarios it could make things worse. Okay, use of a stack to record the most recent page references. I think it's just that, just what we understood out of our heads, we figured that out, but here you see, as 7 is referenced. Here between A and B, 7 is always in a reference, so we bring 7 up to the top. Okay, we understood that. Now we can talk about least recently used approximation algorithms. So least recently used needs special hardware. Why? Because we need a timestamp. Now there's a timestamp idea. The stack we're going away from. This kind of stack is possible and would work, but it's expensive. Then we can go back to the idea of the timestamp. The timestamp is also needs special hardware and it's slow. Every time we do a memory reference, we're gonna have to change. Even though the hardware is fast, it's still gonna mean changing the date. And we're still gonna have to search. So what about an idea like this, a reference bit? Not a whole date stamp of like a, 4 bytes long, but just a single bit. With each page, associate a bit. Initially set the bit to 0. So the page, what does that mean? Set it to 0. It's 0, but it's in memory. It's there. When the page is referenced, it goes up to set the bit to 1. Now it goes up to 1. Replace any with reference bit 0 if one exists. In other words, the first page you come along to, who's still 0. Oh, I should put this down. It's hard to see. The first page you come along to, whose bit is still 0, well, what does that mean about him?
And he wasn't referenced.
Well, it means he was referenced, but he wasn't referenced twice. I mean, assuming we have pure demand paging, if he's there at all, he was referenced. But he was referenced only once. A guy who has a 1, on the other hand, is somebody who's referenced twice. So he's like more valuable. Basically, we're just dividing the world between more valuable pages and less valuable pages, as opposed to every possible valuation. As opposed to, we're not ranking them completely correctly, we're grossly ranking them.
So what algorithm does it use? Does it use the first in, first out?
No, when a page is referenced, we didn't say the algorithm yet. First of all, we say, I'm about to say the algorithm. First, let's get some facts on the ground. The first basic facts are when a page, with each page that's in memory associated to 0. So it's actually getting a 0 when it comes in. Actually, it's interesting. This was actually a confusion on the exam last time. Because people were confused when a page comes in. Let's say a new page comes in. Does it get a 0 or 1? By the way, so far it was 0. It says right here 0. It's 0. Why would it get 1? 1
is when it's referenced.
when it's referenced a second time. When it came in, it was referenced, but it doesn't get a 1 yet.
I mean, I assume that when it comes in, it's given a 0, but then we
Well, that's why
immediately
they-
reference it, so it changes it to a 1. But we just put it to memory.
No, but why did it come in? Oh, you're saying it comes in at 0,
And then we use it immediately.
and then immediately we use it, it goes up to 1.
Yeah.
You see what he's saying? It's slightly different parsha, slightly different way of thinking of it. With each page associated bit, initially 0. When page is referenced, set to 1. It's not clear. The answer is, it depends on the exact,
Depends on
you
the
know,
operating system.
it doesn't really matter. We'll see the algorithm.
Really?
So we have something called the second chance algorithm.
I like that. Cache.
What?
I like that one in cache. That's nice.
Which one?
For the second chance.
You learned it before?
What? We did it in cache in the computer architecture.
No, we didn't.
over when we went over cash, that was one of the things you mentioned.
Oh, I mentioned it maybe.
Yeah, we didn't, I don't know, maybe it wasn't part of the material, but like.
Maybe I
we
mentioned
talked
it,
about it.
because I know it from here.
Maybe.
Generally, FIFO. So what is the second chance? It's generally a FIFO. First of all, we do a FIFO plus hardware provided reference, but we use this bit. It's also called clock replacement. If a page should be replaced, here's the rule, here's how it goes. We'll see an example. If the page should be replaced has a reference bit of 0, so replace it. But if the reference bit is 1, then set the reference bit to 0, but leave it in memory and replace replace the next page, subject to the same rules. So for example, like this. It's a FIFO, so first in, first out. So I'm here, you know, I'm going through, FIFO means I'm going one by one. So I'm here, I happen to fall on the guy who's 1. So he's my next victim. But it's a 1, so I skip him. But before I move on, I change it to 0. And now I get to this guy. He's also a 1. So before I move on, I change it to 0, go this way. This guy is a 0. Now, how could he be a 0? Well, either because when he just came in and we haven't yet changed it to 1 because even though we referenced him, we're assuming we don't change it, you know, or because we referenced him, but last time we went through, I wonder if this would work if he always comes in at 1. Let's say he comes in at 0, but then immediately becomes 1 because we referenced him. And could we still get a 0? Yeah, because we could have gone through him.
But then one previous, I guess.
Could happen, yeah. So now we get to a 0. Oh, so that's this picture over here. Notice we've changed everything to 0. And he's a 0, we're going to replace him. Now, next time we come, if we need to replace another page, let's say sometime in the future, maybe 100 references from now, we need to change somebody. So we'll go here, this will be a 1.
We would not start at the start.
No, we remember where we left off, because it's a FIFO. That's what it means by FIFO. This is our FIFO list.
Isn't the start of it 0? And the start of at the top?
Well, we're starting some imaginary place in the middle here.
Oh.
And we're just, the way it goes is that you go around in a circle.
Okay.
So we're at this guy and we replaced him. Now comes a request to replace somebody. We go to this guy, he's a 1. He's a 1. We come back here to a 0. Well, if there's been, the truth is he doesn't have to be a 0 because there might have been a long time that has passed. The top guy could, in the 100 or 1,000 references that happened until we needed an extra replacement, it could be that he was hit also. So it could be that he was hit and he was hit and he was hit, but he wasn't hit. So I'll go through and change these all to 0. And this guy hasn't been hit since the last time I did a page replacement. So he's old, if I get rid of him. So everybody will become 0 pretty quickly, but they'll also become 1. Assuming that I only have a page replacement every 1,000 times, then what's going to happen is anybody who's still a 0 after those 1,000 times is an old page. And anybody who has been, even though I've wiped them all out to 0, I basically start a clean slate. Every time I do a page replacement, I basically wipe out everybody to 0. I mean, I don't wipe everybody. I wipe out until I find somebody who's a 0. I wipe out people. And you say, well, what about somebody who hasn't referenced for a long time? He'll still be a 1 because it's a little eventually I'll come around to them. So that's the idea of the second chance. Now, would it work if when they come in they're a 1 or a 0? Does it matter?
Not really. It kind of makes some difference against the algorithm.
I mean, no, but I mean, would it make any real difference?
No.
Would still work. Would still work in the same way.
But still.
Because if he's a 0, he'll still become a 1 eventually, because there'll be more references to him. And some people, not like everyone will be 0 all the time. Things will become 1s.
It makes more sense to actually start them off with a 1 because you got some initial immunity and you're just coming in. No, I guess you could put.
You already got immunity because you're skipped.
Yeah, when you're in the back of a queue.
Yeah, you came in at 0. It doesn't really matter whether I leave you at 0 or 1. Because anyway, I put you in now here, and then next time I'm not going to try choosing you. I'm going to go to the next guy.
It doesn't matter.
It doesn't really matter. Okay. So this is also called, I think it's also called a counting algorithm. keep a counter. Oh, this is different, that's a different algorithm. Sorry. Wait, what did we mentioned counting algorithm called clock, it's called a clock algorithm, why is it called a clock? I guess that there's like ticking of time, I don't know. You sort of keep track of time. Anyway, another idea is a counting algorithm. Which says keep a counter of the number of references that have been made to each page. That's what I mentioned to you before. You just say like, how many times has it been referenced? Well, this is a bad algorithm, I think, because. How you'll have to wipe out people at a certain point.
Yeah.
You'll have to have a way of. If this number got above a certain number, then make it back to zero again. But then it could be, no, then it could be close to the number,
No,
it's not that.
you have to have something like after some amount of time, you wipe them.
It has to be time. Okay, least frequently used algorithm, replace pages with the smallest, so once you have this count. So it goes up, you could say, replace the pages with the smallest count, they're least frequently used, right? And the most big numbers, keep them. Or you could say most frequently used, based on the argument that a page with the smallest count was probably just brought in and hasn't yet been used, get rid of the biggest people.
That doesn't really make sense.
You know, what you could do here, it makes sense, here about that, but this one, every other time. Every other time you replace, do least frequently, most frequently, least frequently, most frequently. Anyway, you see that algorithms are just whatever you want to try.
We should make our own operating system.
Each process, so. Oh. Where are we? Oh, okay. All right, we're not gonna finish the slide today.
Those are like 30 something.
How much time do we have?
We have like 3 minutes.
3 minutes? Yeah, we do.
All right, we'll stop here. We'll
That's a
stop.
ton
here.
of slides.
76 slides.
What do you think? We're 3 minutes.
76.
I want to stop here. Well, next time it's a good place to stop because the next is a different topic about how many frames should be given to processes. We now assume that they have 3 frames or 4 frames, but how many should we give? So we'll talk about that next time.
We're like,